So that was the read operation to the buffer objects. For writing to buffers, the OpenCL also use command queues. So we can use command queues to read or write buffer data, to read or write data from a buffer or to a buffer. And in these cases, we're going to generate event for dependencies, or later can be specified as a blocking call. OpenCL use buffer read and write commands and generate events for dependencies, or we can specify blocking read or blocking write. Once the command completes, the host pointer can then be reused. So a programmer can think about that the data storage of the buffer object resides on the device after call completes, although this is not explicitly required by the OpenCL specification. This slide shows the details of the CL in-queue write buffer API call. As we can see that this API takes the command queue as the argument, and the buffer object, and a flag to indicating it's a blocking write or not a blocking write. And also it needs to specify the offset into the buffer to write to, and the number of bytes to be written to the buffer, and also the pointers to the source data where we want to copy the data from. The next three arguments are common for many other in-queue type of APIs, where this will specify the number of events to wait for and with the list of events, and also finally what events will be generated once this command finishes. We show you an example of writing buffer here. So again, we have a array of A on the host side. It consists of 16 integers, and we can use a simple for loop to initialize the values of this array A. Then we create a buffer, and we create a buffer as default both read and write operation, and we specify the size of the buffer. And here you can see that we do not have any other memory flags related to the host memory, so you can assume that this buffer is allocated on the device side. And then we want to initialize the buffer using CL in-queue write buffer. So we supply the command queue, the buffer object we just created, and that is the destination of this write operation. And we use CL true to indicate that this is a blocking write. Offset is set as 0, and we provide the number of bytes to write, and then the host data. So this is the source of this memory write operation. So we're going to copy data from this buffer pointed by A to the memory object buffer on the device. And in this example, we do not wait on any events, and we do not generate an event. The following example shows that how we can create and initialize a buffer and then use it in a kernel without explicitly writing the buffer. This example is in fact what we saw at the beginning of this lecture, but we want to go over it again so that you can have a better understanding. First, we call CL create buffer with a memory flag CL mem copy host pointer coupled with this data pointing to somewhere in the memory, host memory. And what this API will do is to create a buffer on the host side. This is the new buffer created, and then copy the data from this buffer pointed by data to this newly created buffer. Even though this buffer is physically on the CPU memory, but conceptually, we know that we have created this buffer in a global memory space of the OpenCL context, and this memory object should be visible or accessible to all the compute unit on the device side. In the next step, when we use set kernel argument and CL enqueue and the range kernel, we will know that the OpenCL will know that the buffer will be used by the kernel. So in this case, OpenCL tries to prepare the data by issuing direct memory accesses, copying the data from the host memory to the device memory. As a result, the buffer object is in fact pointing to some space in the device memory. So this implicit data transfer from the host to the device is done prior to kernel execution. The runtime, in fact, can also choose to have the device access the buffer directly from the host memory. As an alternative, we can use write buffer APIs to create a buffer directly and copy the data explicitly. So this is what we're going to do. So first, we use create buffer without specifying host related memory flags. So in this case, we actually create the buffer physically on the device side. So you will see in this example, as illustrated, that the buffer object will point to a buffer allocated on the device side. And then we'll use CL enqueue write buffer to explicitly copy data from this host side buffer to this buffer object on the device side. Again, we use direct memory access to improve the data copy performance. After this is done, we actually have the buffer object pointing to the device memory, which now consists the initial data. We now have the buffer object pointing to the space on the device side, which consists of the actual initial data. Reading buffer APIs is a complementary call to writing a buffer, and it reads the buffer back to the host memory. This diagram assumes that the buffer data has been moved to the device by the runtime. So we already have the data here in this buffer on the device side. Then CL enqueue read buffer, which takes this buffer object as one of the arguments, and also the data, which is the destination where we want to read the data to. This API will cause the OpenCL runtime to actually copy the data from the device side to the host side. This is the details about the OpenCL read buffer API. It's called CL enqueue read buffer, which takes the queue as the first argument. It provides the source of the read, which is the buffer pointing to the device memory, a flag indicating it's a blocking read or a non-blocking read, and then an offset into the buffer to read. Actually, this is a typo here. Also the size of the data to be copied, and then the pointer to the destination. So this is a pointer to the host side memory. And again, the last three arguments are for the events, specifying whether this API call needs to wait for any events or generate any event. Now we're going to look at one example. So we have a buffer on the host side called return array, and we want to use this to store the final result when the kernels are finishing their computation. CL mem buffer is the output buffer that's on the device side, and we assume that the kernels put the final results into this output buffer. CL event is to define an event that we're going to use in the read buffer API call. So between this declaration of the read event and this printf, we assume that there's some other code that will invoke the kernel, and it will generate the result into the output buffer. Also, we assume that this return array are filled with all zeros. So when we get to this point, this printf will print out the values in the return array at index number 3. Because we initialize with all zeros, so we expect to see a printed here and in 0. Next line is the enqueue read buffer API. So we call this API by supplying the output buffer as the memory object we're going to read the data from, and we use here in this example CL false as the non-blocking read. So this read operation is non-blocking, and then we supply the number of bytes to be read, and then the destination, which is the return array that we want to fill out. And this API call generates a read event as the output. And after that, we have another two printfs. We have printf B and printf C, and between them, I have CL wait for event, and then we're going to wait for one event, that is the read event. So let's go over this enqueue read buffer API again. Because we have this non-blocking read, so this API in fact will go through, will finish no matter whether this read operation is indeed completed or not. What that implies is this printf at B, this return array is undeterministic, because it may happen that the new data read from the output buffer are not updated to the return array before this printf is printed. And because we have this CL wait for event, this is to wait for this read operation to complete, because this read event is the output event of the CL enqueue read buffer. So the CL wait for event will actually block until this read buffer operation is completed. As a result, this printf C, this will for sure output the final data that's computed by the kernel. So to help you understand this, let me ask you this question. What if some kernel modifies output buffer which has different contents from the return array between the two printf calls? So this one here and here. So in this case, as I explained, because right now we are doing a non-blocking read, so the content in this return array at this point when we print the B is undeterministic. We do not know if this initial value 0 is going to be overwritten with the data from the output buffer. And because we have the CL wait for event, read event, this will block until this read buffer operation is completed. So the final printf will for sure print out the correct result from the output buffer. Now, if we ask you the second question, let's change this blocking flag from CL false to CL true. So if we change this to CL true, that means we are making this in-queue read buffer as a blocking read. Blocking read will not return until this read operation is completed, which means that this printf will not be executed when this read buffer is in progress. So we can know that at this point, when we execute this printf b, for sure this read buffer operation has been completed. So we expect to see the correct output value printed out during this line, print b. Either way, this CL wait for event will get this CL read event, which is now completed. So we proceed on the final printf. So C will also print out the correct return value from the read operation. And you can guarantee that this print B and print C will output the same value if this is a blocking read. In OpenCL, there are some implications of asynchronous transfer. We can copy data from the host memory to the device memory and from device memory back to the host memory. These changes to memory are not guaranteed to be visible. It is not guaranteed to be consistent until an event reports that the command's execution has finished. Such as in the previous example we saw, using events, we can indicate that the command's execution has indeed finished. If you transfer between host pointer and device buffer, you cannot reuse the data pointed by the host buffer until the event associated with the copying has finished. During a transfer between a host pointer and a device buffer, you have to pay attention that you cannot reuse the data pointed by the host pointer until the event associated with the copying has finished. And buffers associated with the context are not with the device.